I want to talk about substitution versus elimination reactions. This is one of the things that can be very challenging for students as they're starting to pick through these two different types, because as we've seen in the last lecture, elimination reactions are very closely related to substitution reactions, and so to decide between what is happening is quite a critical skill to have. And so we need to look at a few things that can help us decide between these two. To do this, I've got another acronym. As you remember, with substitution, we looked at the scene. In elimination, I kind of contorted this a little bit, but there's actually only three letters that are important, B, A, and T. I kind of finish it off with just a couple of other letters over here to make this into the word battle, and so that we can just remember battle scene as our big word that we can use to kind of look at the distinction between substitution and elimination. Now, I said to you that the key thing here is these three letters here, and they're very easy to look at. The B stands for base, the A stands for acid, and the T stands for temperature. You'll notice I put this E of battle in a capital letter. It's really to remind us that this word over here, the battle part, is really deciding what sort of elimination is occurring and if elimination is occurring. If it's not, we can go on to the substitution side over here and we can go and make a decision based on that. So there are actually quite some easy things to look at in terms of deciding whether there's elimination. And the first thing is actually to look at this. The question here is elimination possible? And for that, we need to have the beta hydrogens. So the beta hydrogens are extremely important. If we see an electrophile that does not have beta hydrogens present, then we can immediately eliminate any kind of elimination reaction occurring, and we can go straight to substitution and work it out from there. Okay, so assuming that we do have beta hydrogens, let's look at each of these in turn. So the first thing that we want to look at is the base. Simplistically here, E2 elimination reactions require big, strong, bulky bases. In the examples that I gave to you earlier, or in the previous lecture, should I say, the classic one that I brought up was really the most famous of all the bulky, strong bases, and that is the tertiary butoxide. So this is tert butoxide. And if you ever see this, you can be very, very reasonably assured that what we're heading for using this base over here is some kind of E2 elimination reaction. So that's a key one to look at. It's certainly strong. It's an O minus. We say that O minus is typically around a pKa of 16 when the protonated form, of course, of alcohols. But tertiary butoxide, its pKa is actually more closer to around about 18. It's a little bit stronger as a base due to the inductive effect of these alkyl groups pushing in. So destabilizes the oxygen slightly, and it's a little bit higher. You don't have to, in this course, you don't have to remember that. I'm not going to ask that of you, but it's just helpful. In this course, though, I do need to introduce you to a brand new base, which has the very simple name of DBU. And whilst it has that simple name, it is actually quite a complicated structure to draw. Well, not so complicated, but just a little bit more unusual. So here it is. It's essentially two cyclic rings. The first is like a 6-membered ring over here with 2 nitrogens in them, and there's a double bond between those two over there. And then the hard part is that connecting this nitrogen and this carbon over here is a 7-membered ring, and 7-membered rings are always a pain to draw. I don't often get it right. Let's see if I got it now. 1, 2, 3, 4, 5, 6, 7. Yes. All right. So this is DBU, and its name is 1,8-diaza bicyclo 5,4,0 undec 7-ene, if you believe that. Let me write it down. All right, before you have a panic attack, I don't expect you to memorize this name. DBU is really the most important thing that I'd like you to recognize. I probably won't actually ask you to draw out the structure of DBU in this course. However, I would like you to at least be able to recognize if something like DBU or DBU itself, if I draw this out, that you can recognize that's what DBU looks like. The key here that it is one of our big and bulky bases. It's actually not that strong because as a base, it's using the nitrogen lone pair, which is very much like a pyridine lone pair. But because we've got another lone pair on this nitrogen and they're connected through resonance, so this can delocalize in, can delocalize out like that. The pKa of this is a little bit higher when it's protonated, of sitting around about 12.5. And this is the protonated form of that. So in both cases over here, I've made this assumption that you understand that when I say 18, we're talking about the protonated form. When this picks up a proton, it has a pKa of 12.5. And so now DBU is very often used in elimination reactions. So let's just look at a quick example over here, how we can compare these two. All right, so I've got two examples over here for us to analyze and look at and think about whether an elimination reaction is occurring or not. And so in this one over here, so our first thing is to write down the battle and to decide whether it is a possibility for an elimination to occur. So what we have here is it possible? We've got a leaving group. We can recognize that over here. In that, so that's looking very good. And we have a base in the form of DBU. It's not nucleophilic because it's big and bulky, so it doesn't want to be a nucleophile. So it is a base. Question is, do we have alpha hydrogens? And next door to this, we definitely have alpha hydrogens over there. There's two over there, and there's one over here. There's a bit of a sneaky thing. I'm going to ignore this one now, but that will come back into a later lecture. There's two over here. And so in terms of what's happening, we are happy enough to say that, some kind of elimination reaction is going to occur with our electrophile because all the potential is there. So then, under the base, we have to decide, do we have a nice, bulky, strong base? And the answer to that is absolutely 100% yes. I haven't spoken about the other things that are around there, but this is definitely looking like the clue really was the DBU. We don't have to go any further. And so this is an elimination reaction, and we'll get a double bond over there and a CH3 over there. So what's happening is it's going to be E2 because we've said that. If you want to, we just want to write this, take this over here. I'm more than happy for you to just take a lone pair, draw a random lone pair on this, showing the picking up of this hydrogen, kicking in and kicking out the I minus like that. And so we get our elimination product. Let's look at the next question as well. So once again, we can identify we've got a leaving group over there. And here we've got an S minus, and an S minus is a good sort of nucleophile. And so when we look at this over here, when we go to the BAT battle, the question of course is, do we have the chance of elimination? And the thing here is that an S minus sitting on a phenyl over there has a pKa of about 8. It's actually very weak. It's not a good base at all. In fact, this an S minus is really quite an excellent nucleophile. And so actually this is unlikely to happen. In fact, we need to go to the next part, which is seen, and have a look at this and decide what's going to happen. And over here, we look at the sterics. It's a secondary leaving group. So we do have our electrophile nice over there. The chance of forming a carbocation, secondary carbocation, we kind of a little bit there, and in terms of sterics, a little bit there and a little bit there. So SN1, SN2 are both options in terms of that. But the nucleophile is an absolutely excellent nucleophile, which is really going to push to SN2 without a doubt. And then in terms of the environment, we remember the acronym for that is STAB. So we have a battle scene STAB. sounding pretty violent. In terms of solvent THF, not a polar protic, so we're also looking again at nicely for a SN2. We look at the temperature, it's room temperature, that's SN2. Are there acids and other acids and bases present? No. So this is an SN2 reaction, and the consequence of that is that when the nucleophile adds in, we get an inversion of stereochemistry over there. So that was just a little bit of a sidestep on our elimination reactions, just to remind us and show us how we can look at reactions holistically. All right. The next thing that we need to look at is the A, which is the acid. What do we mean by that? Now, elimination reactions, actually, we can really simplify it very easily in terms of E1 reactions. E1 reactions are almost always going to be where we've got some acid present. And this is a very good example of what that looks like that. So typically, we're going to be using a strong acid like H2SO4. I'll tell you some more details over there. We're going to heat this up, and what's going to happen is we're going to eliminate the water, and we get that as a product, and water will be formed as well. That was eliminated. Okay, so what's happening over here? Now, this is what we would typically call a dehydration. And for E1 reactions, pretty much all of them revolve around the idea of dehydration. And so why that happens is that you need a very strong acid which has a weak counterion. So what is a weak counterion? Well, a very strong acid will have a weak counterion. What we're looking at is really a counterion that is like an O- type of thing. So of course an O- is normally strong. I'm talking about the conjugate base of a very strong acid. For all intents and purposes, here are some very classic examples. So H2SO4. Then we've got the organic version of H2SO4, which is tosic acid. This is also exactly the same type of thing. And then another one that might come up is phosphoric acid, so HOPO4. So this is also, when you remove that H, when it protonates, you end up with an O-, which is delocalized, heavily delocalized, and it's a weak counterion and a terrible nucleophile. Why is that important? Well, in this mechanism, and I just want to do the mechanism of this over here because the textbook, I think, even in a place gets this wrong. In this mechanism, where we're looking at, we've got this strong acid. The question is, do we have a leaving group? No, we don't, but the strong acid is going to make the good leaving group, so that's why we can do an elimination reaction. But the key thing is that weak counterion that we need. So mechanistically, what happens is the acid is going to protonate our alcohol, making it into a good leaving group. So actually, in this very first step, the alcohol is actually the nucleophile. But once that happens, and of course that will be in equilibrium, it's a protonation. Once that happens, we get this, and we've now made that into a good leaving group. And this is where the E1 mechanism part comes into it, in that this needs to leave. And just like other things, it can leave nicely because that carbocation that forms over there is a nice stable carbocation. Not only is it secondary, but it's just outside the benzene ring as well. So the benzene ring can stabilize through resonance that positive charge. So this carbocation over there is actually quite nice and relatively stable. So this can happen quite easily. We're also using some heat, which is driving the breaking of that bond. And now this is quite an important thing, which things get a bit kind of messed up over here. So after this has deprotonated, we end up with HSO4-, and we have H2O in the reaction, the water that left over there. Okay. And what we need is something to pick up this proton over here so that those electrons can go in, and that will give us our elimination product like this. Okay. And the question is, what's going to pick up the proton? Is it going to be water, or is it going to be the HSO4-? And this is something that really kind of tests your understanding of acids and bases in quite an important way. A lot of mechanisms in textbooks actually show the O minus picking up that H over there. But the best base is actually water. Water is a much better base for picking that up. H2SO4, very low pKa, much lower than the protonated form of this over here. Another way to think about it is what happens if you add H2SO4 plus water. We're going to get an equilibrium, and we're going to get HSO4 minus plus H3O plus, like that over there. And think about that equilibrium over there. Which side does it lie on? If H2SO4 is an extremely strong acid, the whole point of it being a strong acid is equilibrium lies on this side over here. So in other words, this conjugate base is not strong enough to pick up a proton to go back to H2SO4, which is why this conjugate base over here cannot pick up a proton. It's not ideal for that. It's actually much better for the water that left to do that part of the reaction. All right, so that gets us over there. So just for comparison, if we took exactly the same reaction and we now did it with HBr, so we start out with our starting material. Sorry, I'm rushing that a bit. And now we add HBr, and we're heating it, and we're doing it in a polar protic solvent. All right, this is normally done in neat sulfuric acid, although water can be present. This over here will do a substitution reaction. Why? Because this will protonate it. This is not a weak counter ion. The Br minus is actually a good nucleophile, relatively speaking, and it will do a substitution reaction. It won't pick up the proton. And so what we'll get is the substitution product. Now, one does need to be careful in all these reactions, because they sit in a little bit of balance. There are always the potential for one or the other product to form. So in this reaction over here, a small amount of elimination may actually occur. It may be unavoidable, but it is still possible to do that substitution reaction in that way. The last thing that we need to look in terms of our acronym, BATTLE, is the T, which is the temperature. And this is really easy. Essentially, very, very simplistically, high temperatures lead to elimination. So the reason for this is actually just to do with thermodynamics, actually. So consider what happens in an elimination reaction. We have something with beta hydrogens that has a leaving group on it, and we add a base to it. The base picks up the proton. We get the R, which now ends up being an alkene. So it's been transformed into something new. We also get the base, which has picked up a proton, and we also then end up with our leaving group. Okay, so what's happened in this reaction is that we've got two components on this side, and we end up with three components on that side. Now, in a substitution reaction, what happens is we just substitute. The base is no longer a base, it's a nucleophile. We just substitute, so we have two on the one side and two on the other. And our famous equation, delta G equals delta H minus T delta S. So this is the entropy value over here. Elimination reactions are increasing in entropy. All right, so we're becoming more disordered because there's more components that are being formed. So as the temperature increases, so this value over here increases, making a greater delta G, which is favored. So higher temperatures end up favoring elimination reactions. So we can look at just two examples. This basically comes from the literature. These are examples from there. So I've got this starting material over here. I'm going to treat it with sodium methoxide, methanol, and room temperature. And then I'm going to do the same reaction, but with now sodium methoxide in methanol, but heating up. So we can do it at reflux. And so this is where this needs to be looked at very carefully. So we've got our battle. We look at this initially and we see, is an elimination possible? Yes, we've got a leaving group over there, which is, and we've got our O minus over there, O minus over there. And so what we have is definitely a chance for an elimination to occur. So then we've got no acid to look at, but we look at the base. And the thing with the base here to decide whether the elimination is occurring is that we've got an O minus, and an O minus is a strong base, but it's not bulky. And because it's not bulky, we actually sit in a little bit of a quandary here. So we do have a strong base over here, but the temperature is at room temperature, which doesn't really favor elimination reactions. And so in this one, we're going to swing and go towards a substitution type of reaction. So we have this, and we're going to get up with an OMe. And so we've made this new carbon-oxygen bond through a substitution reaction. This version over here, we've got the same thing. We do have a base which is strong, but the problem is it's not bulky, and that really is the thing that makes it a little bit more difficult to consider here. But the clue is the temperature. The temperature, high temperature, where there's a possibility of elimination, is more than likely going to start allowing that to form. And so then this product would end up like that as being the alkene. The O minus will pick up the proton, kick in, kick out the leaving group, and we'll get that product over there. All right, so we have now covered the main things to look at between substitution and elimination. The big things to look at, the B and the A, the base and the acid. The base is really important, particularly strong, bulky bases, elimination is going to happen. If there's no base present, but we have a very strong acid, we have to look very carefully. Almost certainly if it's like H2SO4 or tosic acid or phosphoric acid, any of those acids, and there's heat present, we are almost certainly going to do a dehydration reaction, which is an elimination. It's an E1 elimination reaction that occurs. And that's probably the most common and most useful of all the types of elimination reactions that occur via an E1 mechanism. But temperature is really quite crucial to watch out for. High temperatures for E1 and E2 are definitely going to be on the higher temperature range, particularly when we've got maybe a strong base that is not sterically bulky. Good.